I'm going to guess that I'm not the only person in this room who has been paged in the middle of the night because a disk failed on a database server. And I will bet that I'm not the only person here who has been faced with the situation of frantically trying to add resources to my database because got a surge of traffic and it's about to fall over. And I'm pretty sure that there are others in this room who have had the experience of having to tell a customer, you know, I'm sorry, we're going to have to take downtime because I've got to patch the database, right? These experiences have taught us that you can't build a highly available application if you don't also have a highly available database. Hi, I'm Jeff Duffy. I'm a product manager for Amazon DynamoDB. I'm going to be joined today by Tom and Rich from Amazon Ads. And we're going to talk to you about how DynamoDB helps you build highly resilient applications. So I'm going to talk a little bit about what resilience means and how we think about measuring it. And I'm going to talk about how DynamoDB's features help you build for resilience. Tom's going to come up and explain why Amazon Ads chose to move a critical workload to Dynamo to increase their resilience. And then Rich is going to come and do a deep dive on the choices that he made in order to achieve their resilience goals. And so when I talk about resilience, what I'm talking about is the ability to adjust to change. And that change comes in several forms. For an application, usually we first start thinking about it in terms of infrastructure failure, like a disk failing or a server dying. And certainly we need to be resilient to that. But we also need to be resilient to variance in demand, like a surge of new traffic that we have to be able to handle. And by the way, resilient applications should also be able to handle demand changes in the other direction, right? When things get a little quieter. And also, system modifications, and the most common example of this is patching your software, right? Some sort of bug hits and I need to apply a patch. Your system and therefore your database needs to be resilient in order to let you keep operating when you need to do that. And so when we think about the components of resilience and how we'll measure it, these are the two primary types. Disaster recovery is focusing on an entire workload, right? We usually think about DR after something bad happens. It falls over. How am I going to get back to where I was before that thing happened? Usually, after failure. We also think about this in terms of high availability, or HA. And HA focuses on the individual components of our application workload, not the thing as a whole. And with HA, our goal is usually to try to handle the failure of a component and keep operating without having to respond, after the event has happened. So when we think about measuring resilience, the industry typically thinks about it in these two terms. The first of which is our recovery point objective, or RPO. And our RPO basically dictates, how much data am I willing to lose if something bad happens to my database or application. We usually measure it in time. And so, like, for example, if I'm doing backups on a regular schedule as my resilience strategy, and I'm doing them every 2 hours, then I'm going to expect my RPO to be 2 hours, right? I could lose up to 2 hours of data. Our recovery time objective, or RTO, is about how quickly I can get back to normal operations for where I was before. And so these two measures, RPO and RTO, are the goals that we set for ourselves when we build for resilience to know whether or not we're achieving what we're setting out to do. And so, of course, you can ask yourself, well, why don't I just make my RPO and RTO 0 at all times, right? I never want to lose data. I never want to go down. And the answer is cost, right? Because the more resilient we are, the more that's going to cost to do. And not every workload needs to be super highly resilient. We can have dev test workloads where it's okay if we throw the data away. We're probably going to create it again anyway. Right? So at AWS, we talk about resilient strategies in our well-architected program, and we have 4 primary ones that we usually talk about. The first of these is a simple backup and restore, and this is going to have resilience, in hours, right? RPO and RTO of hours, because it takes time to take a backup and to restore it to a new table in DynamoDB's case, and then point your application to the new table so you can get back to doing what you're doing. But the advantage here, of course, is it's very low cost to adopt backup and restore as your primary resilience strategy. The next one we talk about is called Pilot Light, and this dramatically lowers our RPO and RTO to tens of minutes. And this is the one where we kind of cross the threshold between DR and HA a little bit in the sense that we're going to commit to copying our data to multiple places in order to achieve that low RPO and RTO. And the cost for Pilot Lite is typically lower because the general approach to this is have multiple copies of your data in multiple places. In AWS, we usually mean regions, right? But you're only going to have one copy of your infrastructure in one place. You'll just be ready to deploy that infrastructure near the second copy of data should something happen, typically using infrastructure as code tools like CloudFormation to do it should the need arise. And this keeps our costs lower because we only have one copy of the infrastructure running. So the worm standby strategy, now we're going down to single-digit minutes. And the way that we achieve this is that we typically have copies of our infrastructure deployed in multiple regions, but we don't scale them both up all the way to handle production traffic. We usually have a primary region where we're going to have our production traffic there, flowing most of it, and then we might have a secondary failover target region where we'll have a trickle of traffic flowing through, just so we can make sure everything's working. But should we need to shift all the production traffic over, of course, we can do so. And then active-active, right? And this is the scenario where we have a strategy where we want zero data loss. We want zero RPO, and we're willing to bear the higher costs of running significant amounts of traffic in multiple places at the same time, rather, in order to ensure that I can shift my traffic wherever I need at any time. So the underpinning of how Dynamo does what it does in order to deliver to you those higher resiliency features starts with AWS's global infrastructure, right? And I'm sure you're familiar that we have 32 regions, which are the geographic areas of the world where we have resources. And those are divided into availability zones, which are groups of resources in a region that are aligned along failure domains like floodplains or power availability, network, things like that. And then the services that we provide, like DynamoDB, offer regional API endpoints that are themselves highly redundant. So the idea being, of course, if that a sub-regional failure happens within AWS, we're going to be able to handle it transparently, and you can still get to the service that you need to talk to. So when you're planning for resilience, right, we need to start by understanding that just as with security and other parts of AWS, there's a shared responsibility model for resilience as well. And so AWS is responsible for resilience of the cloud, and that means that we're implementing our infrastructure and services to deliver to you the levels of guarantee that we provide, the redundancy that we provide in our networking and our infrastructure in order to make sure that our services are as available and resilient as we promise they are. And it's your responsibility as the customer to have resilience in the cloud. And what that means is that you're following our best practices. For DynamoDB, for instance, turning on deletion protection so you don't accidentally delete production tables if you didn't mean to. By testing the backups that you're taking to make sure that they're doing what you expect them to in order to make sure that the resilience goals you're setting are actually going to be met should you ever need them. So Dynamo has some foundational resilience features that just come out of the box where you don't have to configure anything. It's just the way Dynamo works. And that starts with Dynamo being serverless, right? So Dynamo is a serverless service, which means that you don't have to worry about provisioning resources in order to have your database handle the level of traffic you need. We take care of that for you. Dynamo stores every copy of your data in 3 AZs. When you write a piece of data to a DynamoDB table, we guarantee that it's stored in at least 2 availability zones before we acknowledge the write, and then we eventually consistently copy it to a 3rd availability zone, so we provide you an extremely high level of durability within a region. And then Dynamo provides zero downtime updates, which is a very big deal for a lot of our customers. No longer do they have to worry about scheduling maintenance outages in order to patch the software. We handle that transparently behind the scenes for you. So part of resilience is managing capacity and the need for throughput, and Dynamo offers a number of ways in order for you to manage this. We offer 2 different capacity modes, the first of which is called provision capacity. And you can think of this as 2 knobs on your DynamoDB table that you can turn in order to increase or decrease the amount of read and write throughput that table can handle. Now, of course, most customers don't want to manually manage these knobs for themselves. And so we offer integration with the AWS autoscaling service that allows you to set limits, ceilings, and then targets for your capacity for your database, and it'll automatically scale up and down depending on the traffic throughput that we observe. We also offer on-demand capacity mode. And this is sort of the easy button for managing capacity for Dynamo. It scales all the way to 0. We automatically look at the level of traffic throughput that's coming in. If we notice that you need more throughput capacity than your table has currently, we'll just go ahead behind the scenes and automatically add that for you. And so, of course, you may be asking, well, why don't I just use on-demand all the time? The answer is that on-demand and provision capacity have different pricing structures. Provision capacity is a really good choice if you have very predictable throughput needs that just changes every so often for your database. It's going to be very cost efficient. On-demand is excellent for workloads that tend to have super spiky patterns that also go to 0 at relatively frequent intervals. So another set of features that Dynamo offers are recovery features, right? And these start with the point-in-time recovery. So point-in-time recovery, or PITR, is a continuous log for 35 days of all of the changes that are made to your DynamoDB table. We're always keeping track of those changes for you when you turn PITR on. And you can, at your choice, restore to any second within that 35-day period to a new DynamoDB table. And this protects you against things like accidental overwrites of data in your database, where maybe you didn't delete the table, but a bad code push went and wrote over a bunch of data that you didn't want it to. Well, you can go back in time before that code push to PITR, restore to your new table, and get back to business as you were before. And of course, DynamoDB offers backup and restore as well. And we offer integration with AWS Backup in order to let you do things like schedule your backups and copy them across regions and so forth as well. DynamoDB has a feature called Global Tables that offers multi-active, multi-region replication of your data. And this is nice because there is no primary, and thus there's no concept of failover to implement strategies for resilience. You can write to any replica in any region in a DynamoDB global table at any time that you want, and that change will be eventually consistently replicated to all of the other replicas within that table. This also allows you to increase your availability guarantees from 4 nines in a single region to 5 nines in multiple regions for DynamoDB. And again, you don't need to think about failover. If you want to shift traffic, you just start sending that traffic to a different region replica than you had previously. And so if we think about the strategies that I talked before and then the DynamoDB features that I just described, and we put those together, this is what it looks like to implement some of those resilience strategies with DynamoDB. And of course, when we start with backup or restore, right, that's going to be the PITR feature that I described before. Of course, PITR's running, tracking your changes over that 35-day period continuously. And of course, you can schedule backups with DynamoDB and AWS Backup Service in order to make sure that you're going to have backups at regular intervals if that's the strategy you want to adopt. Now, when we talk about the pilot light strategy, again, remember, we're talking about copying that data across multiple regions, and the easiest way to do that in DynamoDB is to use global tables, of course. And so what you'll do in a pilot light strategy, and remember, this is the one where I'm going to have all of my infrastructure deployed in one region, and then I'm just going to have a copy of my data in that other region, or maybe a very minimal set of resources. And so what you can do is that you can have your global table replicas replicate your data to that second region, but you can scale it down if you want to a minimum level in order to conserve costs, or you could just leave the table in on-demand mode if you're not going to use it, and we'll handle scaling it down for you. The warm standby approach then can be implemented also with global tables. And remember again, this is just, the change here is going to be that you're deploying more of your infrastructure in that second region. So Global Tables is already doing that replication for you. It's already handling changes to whatever region that you want to make the changes to. And what that means is that you can have that trickle of traffic always flowing through that second region to guarantee that your infrastructure is working the way that you want to, and still be confident that your data is going to be consistent in your primary production region. Finally, when we talk about active-active, global tables replicates in an eventually consistent fashion, and so it cannot deliver an RPO 0 guarantee because it takes some time to replicate that data to another region. However, I talk to a lot of customers who say, I don't need RPO 0, I need RPO 30 seconds or RPO 1 minute, and global tables generally replicates your data in much less than a minute, especially if you're staying within a given continent. So you can implement an active-active approach with global tables, just not quite zero RPO. If you need zero RPO, then the approach you're going to have to take is to have multiple tables in multiple regions and write to both of those as your application works. And of course, you're going to be able to manage that capacity by, in that case for active-active, fully provisioning the replicas to the level of traffic that they're going to need in order to process your traffic, or as I said, simply use on-demand and we'll handle that for you. And now I'd like to turn it over to Tom Skinner, who's going to talk about how he and Amazon Ads have decided to use DynamoDB. Tom?
Thanks, Jeff. Well, folks, we made it. It's the last session on the last day of reInvent. So, I'm Tom Skinner. I'm a director of software development for Amazon Advertising Measurement. And I will be presenting today a little bit of a quick overview of Amazon Ads, a discussion of one of our most critical workloads that we moved to DynamoDB, and the results that we have achieved. Amazon Ads' mission is to help build brands and businesses of all sizes while creating ad experiences that are useful for our customers. We serve advertising on and off Amazon properties across connected video devices, web, and applications. At its most basic form, advertising drives discovery. Advertisers use our advertising programs to build awareness or increase shoppers' consideration of a certain product or service. These advertisements can be about a product sold on or off Amazon, and we serve advertisers and agencies in all industries, including financial services, travel, entertainment, and more. Advertisers use our analytics and measurement to plan marketing strategies, serve and optimize ad delivery, and measure advertising outcome. Because advertisers are using our measurement to make investment decisions, it must be accurate and near real time, especially during those peak events where they're optimizing several times throughout the day, such as Prime Day. Given the importance of ads measurement to our customers, our infrastructure must be resilient to both service disruption as well as infrastructure failure. In addition to these calculated metrics, we also calculate a data age, which is the entire time in which it takes the pipeline to calculate the metric and make it available to our customers. As I said, one of our most critical workloads that we operate is our attribution algorithm pipelines. Attribution is the way that advertisers determine how marketing tactics and those subsequent customer interactions contribute to sales, conversions, or other goals. Attribution is one of the ways that customers answer the question, what was the return on my advertising spend? An example might be a shopper looking for a TV. They'll come to Amazon, they'll search and browse and look at various detail pages comparing various models. Eventually, they may click on a sponsored ad listing and purchase the TV. Our algorithm must consider all of those interactions, views, clicks, and determine which one receives credit for that purchase. Then they'll use our reporting systems to view that performance and gather valid metrics such as return on ad spend, which is the ratio of ad spend to sales. Some of our traffic sources have predictable bell-shaped curves, roughly matching browsing behavior, increasing throughout the day and decreasing or slowing in the evening. And they also may increase many times on high-volume days, such as Prime Day. We also serve advertising for video advertising, such as Thursday Night Football. These events have unpredictable spikes where we can deliver many, many millions of impressions in the span of 90 seconds or less, followed by random periods of quiet. To make things interesting for the team this year, we had both a football game and Black Friday on the same day. If we connect these concepts back to Jeff's introduction, our infrastructure must be resilient to both constantly changing demand, and our infrastructure should be ideally completely elastic and react automatically to these peak demands. DynamoDB on-demand capacity is one of those great features that allow us to hit the easy button. To give you an idea of the scale of the data that we process and workloads that we have within ads measurement, we have over 4 petabytes of data in DynamoDB. We process more than 100 billion events daily, and our peak DynamoDB throughput is more than 90 million RCUs and more than 5 million WCUs. To compute attribution, the algorithms require a lookup of all relevant traffic for the previous 30 days. This lookup requires us to do high-scale range scans filtered on date and other identifiers, and trillions of those ad identifiers must be searched in a sub-second query response time. When these algorithms were originally built, we chose HBase as the chosen technology, and in order to scale query throughput over time, we replicated these H-based clusters on AWS EC2. As you can expect, managing these hundreds of nodes, even with automation, was very painful for our engineers. To support those use cases, the team had to add custom modifications to H-based code, which also made our software upgrades very time-consuming and expensive. The cluster ran on EC2 nodes in a single region on older generation hardware. And so we would have at least one unplanned cluster outage every sprint due to hardware retirement or other hardware failure. And the cluster was also in a single region, so we were exposed to those AWS instances as well. Because we managed our own cluster, we had to scale in large steps well ahead of peak, accruing unnecessary costs. HBase has this lovely feature where you can add nodes, but in order to remove them, you have to rebuild the cluster. Not. In late 2022, we set on a journey to migrate our storage layer to a new technology. The team had 4 high-level requirements. First of all, we had to do this migration with 0 downtime to our customers. As I've stated, attribution is critical to our customer experience, and they expect near real-time performance. So we had to do parallel runs, we had to do data comparisons so we made sure that the numbers weren't changing for our customers. Second, the new system had to have the same or lower level query latency. To enable this cutover, we implemented a service layer in our data pipelines so that we could change the storage layer without having to change the data pipelines. This service layer added latency, so we had to make it up in other ways throughout our data pipeline. We wanted to use a managed solution if one was available. The team currently had about a 3-month ramp-up period to be essentially a software engineer expert on HBase. We wanted to eliminate that. So we also introduced additional availability risk every time we had to do HBase server upgrades. And finally, we had an aggressive migration schedule. We only had budgeted about 30 days to do the full migration due to parallel system cost as well as operational burden on the team. So what did we do? We first refactored our data pipelines to incorporate and eliminate the heavy HBase client that directly talked to the customers and implemented a service layer built on ECS. Then this new service layer gave us a layer of redirection, allowed us to do A/B testing and latency evaluation as well as data quality comparisons through CloudWatch. It gave us rollback capability. And next, we pointed our ingestion process to dual write mode, and we loaded both DynamoDB and HBase at the same time. However, this started accruing migration costs, and so the countdown clock was started. We completed the cutover within our 1-month budget in early April. And at the end of this month, we tore down our legacy HBase clusters, deleted the code and alarms. We actually had a huge party for all of the team members, including past team members and managers, where we essentially had what we call our dead cake for the team, which we always celebrate whenever we kill or deprecate an old piece of technology. Since the April cutover, we've seen the following results. Our availability has increased from 4 nines to 5 nines when we enabled global tables. Developer ramp-up time is reduced from 3 months to 2 weeks. They no longer have to become HBase experts. They can just focus on their business logic. Since the migration, our ticket load is reduced by 40% on the team. This allowed the team to take on 2 additional charters with no additional headcount. Finally, we did this in a completely cost-neutral manner. Our cost for the AWS managed solution is less than the cost of our hand-managed HBase clusters. Now I'd like to turn it over to Richard Edwards, the principal engineer on my team, who designed this migration, and he'll give you a deeper detail on the Dynamo.
Thanks, Tim. Hi, everyone. I'm going to tempt fate here, but I do want to highlight one key thing before I dive into this. This system is operated through 2 worldwide global events with 0 operational pages for its engineers. We're talking about Prime Day, Turkey 5, and then a local event of Diwali with 0 pages and 0 operational load on the team. And so let's go into it. So I want to highlight the problem that Tom was talking about first. This is what we call the internet scale join. Essentially, we're taking purchase events or any other things that we call conversion events and joining them with ad interactions. And that can be quite a large one. So let's take an example and put some data numbers to it. So if we look at 100 billion events a day, and we join to the last 14 days of data, we're talking about 1.4 trillion events. If you were loading that into memory or on a EMR cluster and running a Spark job, and those are 1 kilobyte each, that's 1.4 petabytes of data. And if you're doing that on an hourly cadence, that's not practical. And so what we did way back is we inserted HBase. We decided to pre-index the data and make those fetches efficient. And this allowed us to scale out and continue to grow as ads grew. And so this made it efficient, but we were hand managing HBase here, which was creating some operational pains. So as we looked to replace it, our functional requirements were lowering the operational load, retaining higher availability. Basically, every time we would go down, customers weren't getting metrics, and so we needed to be able to either never go down or be able to recover very quickly. But the more critical one is we can't afford data loss. Our customers depend and make critical decisions off of this data, and the data has to be right. So losing any data means that we're reducing the quality of the results to the customer and we're diminishing their ability to make decisions. And more importantly, support all existing workloads. We didn't have a single workload that was running that we believed we could turn off. They were all critical and all important to a customer. And so our solution is to take HBase and replace it with Dynamo. Now, that seems like a very simple conclusion to ride, but we actually worked with HBase for quite a long time. And we made serious engineering investments before we reached this decision. And so I want to walk through some of those to give you an idea of what we were operating. And so these are our HBase operational issues if we had to pick our top 4. Availabilities on redundancy, disaster recovery, query load balancing, and just basic cluster maintenance. You'll imagine taking down a cluster, updating it, was actually not very straightforward. It was generally about an 8-hour process. And so let's look at availability zone. As Tom mentioned, we replicated our data. So we had hand-managed replication configurations across our clusters, and each cluster was striped into its own availability zone. Now you're thinking, well, why aren't they all in 3 AZs each? Well, the problem is that if one AZ goes out and each one is striped, and they all use that same AZ, you just take 33% of your capacity out of all your clusters. And so we followed the EMR model of every cluster fails independently, so that when we lose one cluster, we remain 2/3 of all of our capacity. However, fun thing about managing your own replication, if the one in the middle of the chain goes out at 2 in the morning, your engineer has to wake up and manually edit replication strings to recover replication between availability zone 1 and 3. Not fun. And then there's also query load balancing, the tick client that Tom mentioned previously. This allowed a query to execute against any of the cluster giving results and managing the load. However, you can imagine in this configuration, if a cluster goes down, well, the thick client will retry, but it could still go back to the bad cluster. And so you're getting woken up at 3 a.m. to take out a cluster out of service because it's failed. Well, that's silly. So we added an automatic cluster removal capability using Lambda and cluster health metrics. When a cluster went unhealthy, we removed it from service automatically. And so now an engineer is getting paged at 3 in the morning to fix a cluster, but the customer's not impacted. So slightly better, but not great. And so what really is here is the cluster ownership overhead is what really causes a lot of headaches. The custom HBase builds, ramping SDEs on HBase and its internals, but more importantly, SME, or what we like to call subject matter expert blast radius. So this picture on the right is me on vacation halfway across the world. After an hour after this was taken, I was paged. A routine maintenance went south and they couldn't get a cluster back online. So I don't know how many of you have been on vacation and you just get a reach out page and say, hey, I need help. And that's what happens with HBase for us at least. It takes very specialized work for our engineers to understand and operate it because they have to know the internals deeply, just to even do basic cluster maintenance. But then the real major second pain point is low elasticity. As Tom mentioned, we're dealing with multiple variable workloads and we always have to be prepared for the worst. And so we were consistently overscaling and over-provisioning, which is just not financially efficient. And so DynamoDB solved these pain points for us. There's no OS, there's no security patching, there's no redundancy management, and it's fully elastic. So we're able to control our costs by scaling up and scaling down accordingly. And me, selfishly, I can go on vacation and not get paged, which is a win for me, and definitely a most for our engineers as we continue to grow the team. And so, but to get these results, we're going to go through 2 consideration categories that we looked at: table structure, throughput, and table management. Now, these are all interconnected. These all impact resiliency together. You can't have one without the other. And so if your table structure is good, great, you can get good access. But does that mean you can get good throughput? And as you start looking at table structure and throughput, how do you manage your tables? Do you need one, two, multiple tables, GSIs, GTs? All of these things matter. And so when you put these two together, they really come back to Jeff's point on the shared responsibility model. We as customers of AWS, we are responsible for the brown portion of this box. We have to build applications that can work within AWS's supported limits and make sure that our applications can stay available. And let's look at what this looks like from an application standpoint as a naive toy. We have a predictable load and application in DynamoDB. As we change that load, the application may keep working, but if we have a bad design, it could fail. DynamoDB won't fail. They guarantee you the resiliency and the capabilities to stay available, but your application may fail. And so that's, on the shared responsibility model, it's up to us to design and avoid those failures from either timeouts, retries, et cetera. And so as we walk through table structure, let's look at our workload of how we are looking at data for our application. 20% of our workload is query all interaction data, regardless, no filtering, no criteria. 80% of the workload is targeted filtering of data and selection. And so let's visualize this to make this a little more concrete. So if you look at this block, we have a partition of data with a partition key, a sort key. And so within this data, everything is related to that partition, and you have nice grouped blocks on the attribute. And everything under that attribute is time sorted. And so this is the way that we actually looked at the data on HBase, and this is how our data was laid out. This is just data in terms of Dynamo. And so what we really looked at is when we looked to migrate is we had 3 time series schemas we can consider. What we call fully sorted, partially sorted, which we just saw, and then scatter sorted. And then let's see what these look like as a table structure. And don't worry if these are too much to take on this slide. We're going to walk through each one with a detailed data example. And so we had to decide which one of these we wanted to implement and which one was going to be best for our application and our customers. And so the partially sorted we looked at, which would be a lift and shift for us, you could see that we have the ability to access and filter directed data perfectly. If we want to, though, be able to support the other 20% of the workload, the customer has to read the data and resort it, or in Dynamo terms, add a GSI to get a fully sorted view. Now, this is what it looks like from a query view. You can specify a single data piece, and you'll get one query result. If you want to do multiple queries, you start also encountering a high throughput risk. If I need to select 20, 100, or 1,000, I have to execute a query against each partition key, which is the same, so I'm increasing my risk of hotkeys. And that's why we're calling this a throughput risk. And you have to execute all of those queries in order to get every piece of relevant information. Now there's the fully sorted version, which is a little nicer. All of your data is just time sorted. You throw away the ability to filter select and you just say, I'll read everything, and then I can make client-side filters if I need to. And so what this looks like when you query is pretty straightforward. If I want to query 20 items, 10 items, 1,000, it's just one query, one connection. However, there's still a throughput risk attached to it. If we start ramping up a lot of queries externally, and we get a lot of queries for the, say, ID 1 in this example, we still could get a very unfortunate hotkey incident. And so that's still a throughput risk from our perspective. Now there's the scatter sorted, which tries to distribute the keys by the partition and the attribute. And so now we can still subselect data, and we can scatter it so that we reduce our throughput risk. So let's see what it looks like when we query. We're essentially saying that each key, no matter which piece you're subselecting, you're going to a random partition underneath. So you're repeatedly hitting the same key. And so this is going to reduce your throughput risk. And so this looks like it'll work. It'll solve 80% of the workload, but what about the other 20%? Well, we selected this and we tested it. And the way we solved the other 20% is we added a GSI. DynamoDB supports this out of the box. I don't have to write any additional code. It can replicate and pivot the data for me. And so with the GSI, I have the other 20% of the workload, and I have the 80% on the primary table. So we should be done, right? Well, not quite. Query amplification. This isn't a DynamoDB concern, this is an application concern. There's no DynamoDB throughput, but each of those scattered pieces is a query. And if I have to run 100 queries, that's okay. For a small workload, it might be fine, 1,000. But what if you got to do 20,000, 100,000? These are the things we started seeing when we push scale. And so what it really looks like from an application point of view, this is query amplification. For one request, you're running multiple queries either in parallel or serially to try and service the request. And at high scale for Amazon, it doesn't work. And so we were back to the drawing board. And so what we ended up deciding with is, let's use the one that has no query amplification, but has a throughput risk. Let's find a design that removes the risk. Because this is a very simple application concept for us from a query amplification standpoint. One query, one request to Dynamo, and then we just have to solve to make sure that we don't get throttled based on how we set up the rest of the data. And so this is what brings us into our actual selection is fully sorted. It gives us a simpler query paradigm and allows us to service all of the requests with one risk. And we're going to solve it. And so that's why we talk about throughput. We've selected a design that has a throughput risk. But can we solve it? And the answer is, of course, yes. And so here's your default throughput constraints. DynamoDB will support partition, 3,000 RCUs strongly consistent, 6,000 eventually consistent. And for our applications, we're entirely working in the eventually consistent space. And so a very simple way to increase that, write more copies of your data. Just writing 3 copies of this data would triple your throughput. Assuming you can uniformly query across the copies, you now have more throughput. And because you're writing the same copies, you're actually increasing your strongly consistent and your eventually consistent. So now that rather than having 3,000 and 6,000, we have 9 and 18. But we can get even fancier. We can use GSIs to create read-only replicas. Now, a read-only replica for a GSI won't increase your strongly consistent throughput, but it will increase your eventually consistent, assuming you continue to uniformly distribute. So now we have 36,000 RCUs. So we're starting to push the fact that I can get more throughput out of hitting a same key, in our case, if I just uniformly distribute across my copies. And then we can go even further and do the same thing with a GT. And the GT gives us an extra added advantage. Not only am I copying my data, but I also have gained a regional redundancy. If a region was to go down, I'd still have data available in another region and could access it. And so you'd have reduced capacity, but higher availability. And so we can get even more extreme, and we can go to a static replication plus GT plus GSI. Now, this is a bit odd example, but to just put it into perspective, eventually consistent throughput on this, if you balance your queries properly, is 72,000 RCUs. That's a really big number. It's bigger than actually what we need it, but it's just showing that it can be done. And so if you want to put that in data terms, it's about 288 megabytes at 4 kilobytes per RCU for a single partition key. That's a lot. And so this is what we ended up using. This is our production setup. 2 static replication, 2 GSI read replicas. This gives us 36,000 RCUs eventually consistent throughput, or 144 megabytes per partition key approximately. Now, this is all theoretical. You won't actually hit the max because you'll also have other keys competing for the partition, but in theory, you have really significantly reduced the likelihood of throttles from repeatedly hitting the same key. And so how do we decide this? This seems odd. How do you know this is right? Well, we did A/B testing. We tried different configurations and different setups, such as just deactivating one of the GSIs, because we've written the ability to uniformly distribute our queries, turned one off, tested it. If it worked, great. If it didn't, try a different configuration. And trial and error basically allowed us that this was the right cost profile and ability profile for us. Now, there's a catch here. What I described on the previous slide looks kind of fixed, especially with static replication. That's one of those things that you have to set up right away. So now we're really going to talk about table management here. Are there one-way door decisions in that setup? And so in Amazon, what we mean by a one-way door is an architecture is inflexible, or it's very hard to go back through that decision. And I think if any of you as developers or as SDNs for software development managers, the last thing you want to hear from an engineer is, well, it works, but I'm going to go have to redesign it if we want it to work better. That's really not an answer you want to hear. You really want the architecture to be flexible, able to do more. And so this is where things got interesting. How do we grow throughput? How do we shrink throughput? Because we showed the static replication that it's giving us high throughput, but do I need it all the time? Do I need it for all the data? And so if you look at our configuration, well, the simple way to add more throughput is I could add a third replica. Okay, how long does that take? Well, let's say you stored 100 days of data, it would take you 100 days wall clock time to queue that additional throughput. That's not great. Okay, how else could I get it? I could write a tool that would replicate all my data for myself. Okay, that's going to cost money because you got to go read all of your data out of your table. You got to then write it back. That's not great either. So how can we do this through table management? Well, if we look at what our table set looks like now, we basically have a primary table and 2 GSI replicas. What if I use DynamoDB's existing features just to add a new GT on the fly? Let it copy the data for me rather than adding more static replicas. And in essence, what this is doing is now we're flexible. We can grow our capacity, or we can add another GSI replica. We've now replicated the data in another direction. And also, we could take that capacity away by deleting a replica. But it looks great on paper, and so then you really run into this in configuration. You can have as many AWS regions, as many GSIs as you want to grow and shrink your replication to grow throughput. Sounds great, but do I want to replicate 4 petabytes away from one AWS region to another? How long will that take? It might be faster to drive a truck from one data center to the other to move 4 petabytes of data. So it's not really great from an actual service availability standpoint. And so if we really think about it, we sharded our table. And so what we're actually operating on, rather than a single table, is many tables. We've split the tables such that I only need to replicate a subset of the data or a component that actually needs the additional capacity. And the way we did this is just simple. Mod. The mod operator, just to your primary key, tells you which shard to use. And so you're thinking, well, how do you know you have enough shards? Well, what we did is we just said, here's our data growth, here's our projected curve. We're going to just make it large enough so that we don't need to resize this thing in our lifetime or the next generation's lifetime. And so we have sufficiently a large enough number of tables that we never need to resize it. That was our design philosophy to avoid that challenge. And I'd love to be wrong there because then that means my business is doing awesome. And then we'll go solve it when that problem arises. But what this has allowed us to do is to pivot how we think about tables. We now look at tables as a table set. We've built a utility called the Table Set Manager. Really, each table is a shard, and it can have any state. It could have a GSI, it could have no GSI, it could have GTs with no GSIs. Everything can be configured independently at a smaller grain of data. And so the time that it's going to take to create a replica is significantly reduced. And so this is giving us the flexibility to control our cost and scale at a more fine grain than if we had just done everything as a single table. And so what this has allowed us to do is we're operating in a pilot light mode. We have sufficient copies of our data that we can operate and sustain high throughput increases or failures. And if we need to, we could evaluate moving to warm standby and active-active. Those options were never available to us on HBase. Because we were hand managing our clusters and capacity, we were significantly constrained by our own architecture and understanding of it. And so our application view is shifted. We have variable load, we have our application, but DynamoDB no longer looks like a silent DynamoDB instance to us. It's now an elastic set of DynamoDB tables that we're growing and shrinking as needed to meet our demand and continue to grow and improve our business. And so what this has allowed us to do is generating really great results. And so let's talk about this. We are hitting 80% of our capacity utilization, so very low waste. But more importantly, 0.008% throttles per 60 million RCUs. As Tom mentioned, we're using 90 million plus RCUs at peak. So you can imagine that's a very significant low amount of throttles, which means very low disruption to our customers and our clients using our service. But more importantly, with better operational recovery. And so if you look at this slide, one of our customers was having a bad day. A software deployment went bad and our capacity utilization plummeted. If this was on HBase, the recovery, which you see is quite sharp, we would have been hand managing and helping them recover through joint operational efforts. With DynamoDB, we didn't have to do anything. We were able to watch them recover, roll back their bad software deployment, no intervention from our side. And so that's a really good win for us from an operational standpoint. And so in conclusion, we have high availability and high throughput. And we're on a pilot AI operating model, which is allowing us to have higher redundancy and better control over our availability for our customers. And which also gives us the dynamic throughput that we need to control our cost. And cost is pretty important because at our scale, a small change could have significant financial impacts. And so what's next for us? Where are we going? We're going to evaluate pilot light to warm standby and active. As we continue to grow and the importance of our workloads increases, the ability to tolerate downtime or failure is going to be less tolerable. And so we may enter a world where having 5 minutes or 10 minutes of downtime or a blip in availability is no longer acceptable. We need to be able to guarantee that we're always on and always available. But then more importantly, this design pattern we're going to double down on. We found multiple applications within our own org and across ads that could use these same viewpoint and lens in order to improve and decrease the operational loads on their teams and better utilize DynamoDB. And so I'd like to turn it back over to Jeff to give a summary on his three key takeaways. I hit the button again, sorry.
Thank you. So if you take 3 things today away from our discussion, they should be these: that you can't build a resilient application unless you also have a resilient database, and that DynamoDB offers you a very rich set of resilience features to allow you to build applications to whatever level of resilience you need. And finally, AWS underpins DynamoDB to help you build for resilience for your entire application and not just for Dynamo. I'd like to thank everybody for coming today. Your feedback's really important to us, so please leave